On this video, I'm going to show you how to solve the ALEKS problem called using the general properties of equilibrium constants. And for this problem, you'll be given a chemical equation and the value of the equilibrium constant K, and then it's going to ask you three different questions about the problem. The first question is going to be something along these lines where it's asking you to make a prediction about the relative amounts of reactants or products in this particular system. And it's asking you, what can you say about the composition of the mixture at equilibrium? This information that it gives you prior to that sentence is kind of irrelevant. It doesn't really matter what you start with or how big your container is. If it's asking you to describe what things are like at equilibrium, then your starting information is really irrelevant. What's going on at equilibrium? We make that prediction based off of the value of K, or the relative size of K. If our equilibrium constant is large, and by that we define as being something greater than 100, that means that we have in our system more products than reactants. This equilibrium constant is large, it is greater than 100. That means that we have more products than reactants, so that means we have more NO than N2 or O2. So the way that the answer that we would select that would be the most appropriate, there will be very little N2 and O2. Mostly going to be NO. Now, even though it doesn't apply to this problem, if your value of K is small, and we define that as being less than 0.01, in that situation, you would have more reactants than products. And if your value of K is somewhere in the middle, so somewhere between 0.01 and 100, then we say we have a pretty even balance of reactants and products. The next two questions, it will ask you to calculate a value of K for a slightly different chemical reaction. It's going to have the exact same molecules. They're just either not going to be in the same order, or their stoichiometric coefficients will have changed. In this particular one right here, when we compare this equation to the provided equation, we can see that it's just been turned around. So the reactants are being written as products and the products are being written as reactants. When an equation is turned around, then the value of K is inverted. So if K is 1 times 10 to the 3, then when we turn the reaction around, K is going to be 1 over 1 times, why did I write 10 to the 1 times 10 to the 3. So when we turn the reaction around, we invert the value of K. Don't enter it into ALEKS like this. We want to enter it in as 0.001 or 1 times 10 to the minus 3. And in this second one I have here, I have my reactants have not been moved. So my reactants are still reactants and my products are still products, but the stoichiometric coefficient has changed. The stoichiometric coefficient has doubled. So when you make a change to the stoichiometric coefficient, you make the same type of change to the value of K, except for it's in the exponent. So if our K value in this case was 1 times 10 to the 3rd, whatever change we're making to the stoichiometric coefficient, so in this case we're multiplying the coefficient by 2, we're going to raise that K value to that particular exponent. If our stoichiometric coefficients were being multiplied by 3, then we would be cubing our value of K. If our stoichiometric coefficients were being halved, then we would have the value of K, half the value of K, or we take the square root. And again, don't enter it into ALEKS like that. You definitely want to work the math out on this. So this is going to be, I did it to the 3rd, 1 times 10 to the 6. I don't need to use my calculator for that. 1 times 10 to the 6.